and you should be able to hear us. Justin, Javier. Yeah, okay, good. Then today I want to talk about quantization. Last time we talked about pruning of network weights, right, in order to make the network smaller. And we discussed the fact that based on your compute hardware, there's kind of different priorities that you want to set and different approaches you can take. For example, if you have a GPU-based approach, then actually pruning the individual weights doesn't really help you unless you have a GPU that supports sparsity, sparse matrices. With quantization, so by pruning we mean that we take individual weights and we remove them from the network model, right? So you set individual weights to 0, or you take entire rows and set them their weights to 0, which will then remove a neuron. With quantization, what we want to do is, instead of completely removing some weights and leaving the other ones unchanged, we would like to remove the amount of data that we need to use in order to represent and do the inference in the network. So it's an approach to reducing the size of the network by changing the representation of the weights, rather than setting some to 0 and removing them and leaving the other ones unchanged. The most common quantization that you are probably familiar with would be floating point to integer quantizations, right? So you take, at the moment, for our networks, the networks that we trained, I think I used FP32, the single floating point value as a representation for the network weights, which means it's a 4-byte 32-bit data type. We would like to change that to something smaller. Now, first of all, when you look at trying to measure just the effect of the quantization, it's a little bit different from pruning, because with pruning we were mostly focusing, or what should we optimize for? What were we trying to do with when we quantize a network? What would be the goal? Pardon?
Make it like faster.
Faster, okay. And make what faster? okay? But when we think about the neural network, there's two separate phases, right? One is the training phase, the other one is the inference phase. Most of the time, as consumers, we're interested in the inference phase, right? So we want to improve the inference speed, and in there's also two possible parameters that we could look at. One would be the kind of throughput, how long it takes to actually run an inference. And the other one would be the latency. How long does it take after, especially in a robotics domain where things are real-time problems, how long does it take for your network to actually output a particular hypothesis for the car, right? That would be the first part, but depending on what you're trying to do, you may be also more interested in the entire throughput of the network. So if you analyze a video stream and you can process 40 frames per second or something, then that would be also one feature. If you need to, for example, there's actually an interesting book by Heinlein. I don't know if you know Robert Heinlein. He's a science fiction author. And he has a book about the near future. And in that book, the richest guy in the world, or one of the richest guys in the world, like the Elon Musk of the world, the way that he made all the money was by taking the old movies that people still liked, right? So like Star Wars. Star Wars is a great movie and everybody likes it. They want to continue watch it. And then to adjust it, to adapt it to modern sensibilities. So his thing was he could remove people smoking because in the 50s, if you watch a movie from 1950, 1960, they're always smoking, right? But nowadays, it would look odd, like people wouldn't like it. So he made like billions of dollars just taking movies and removing the smoking scenes and replacing it with something else. So if that's your application, then the latency is not really such a big problem, right? It would be more the throughput. How many frames per second can you go through? And I actually think there may be a business model in this in the future. Not just with smoking, but also drinking, all kinds of other behaviors. If you can intelligently replace those, then there may be some money in that. So, but just as an application, then you would be more interested in throughput. In robotics applications, we mostly care about latency. But depending on how you design your network, you can optimize for one over the other often. So that would be the main sort of goal for optimizing and using our quantization. Anything else that maybe we may want to do or that we're interested in? Especially when you think about large language models. Another way that we could use compression would be to reduce the size on disk of the actual model, right? Especially with the large language models. You may have heard MOE with the latest models. What is that? MOE. MOE LLM. That's mixture of experts approach. And so, for example, one of the top models at the moment is Q1, the Chinese one, 3.6. If you look at their descriptions, they look like that. 35 billion parameters, active 3 billion parameters. 35 billion, 3 billion, 27 billion and 27 billion 8-bit floating point. So here we have two quantized models, right? This is floating point 32, this would be floating point 8. And the sizes of this for text-to-text only part would be 3 megabytes. Right? Oh, this is quantized to something else first. And what this here means is that figure here. What we have here is the 3.5 model has 397 billion parameters, so that's 397 gigabytes approximately, right? Even with some compression built on top. So this is a large, actually let's have a look at what the actual size is. 4 billion, yes, yeah. Yeah, I mean, that's what this course is about. Even with those, you can do quite a lot of interesting things. There's been, if you look at the files, there are like 9 gigabytes here, but a whole bunch of them. So that's what you actually had to download. There's been a controversy about Chrome, Google Chrome, which actually now downloads a 4 gigabyte file just when you run the browser without asking you anything. And so they want to do some part of inference for AI models now using this built-in model that you have in your browser now. A lot of people are very upset, especially if you have a small computer, if your browser all of a sudden uses up 4 gigabytes for an AI model, then at least Google should have asked you, right? I think. I don't think it's powerful enough to do that. I think they probably steer it to generate something for you. That's another problem. Nobody really knows what they're using that 4 gigabyte file for what they use that model for. So anyway, back to this kind of specification here. This means 397 billion parameters. So a huge network. Active 17 billion. So this is this idea of a mixture of expert approach, QVen 3.5, 397 billion, active 17 billion, right? Yeah. So here we have a huge network, but at any time, there's only 17 billion parameters that are active when it does the inference. So this entire network would sit on disk, and then it runs the first couple of layers, then it decides what other layers it wants to run. And then those are only loaded into your memory, and then those are what actually running. So you only need about 17 times 4 gigabytes of VRAM if you want to run this on a GPU, right? So in this case, if we can compress the size of the network on disk, then that would be a huge win, and we can do that using quantization. Now, one other comment that I wanted to make, when you look at the benefits, trying to evaluate the benefits, then what metric will we use? Like here, we talked about inference speed, right? So we would look at the time that it takes to do inference, how many milliseconds, or how many tokens per second your LLM can produce. However, with and that makes sense for a lot of applications. Nowadays, however, if you look at one of the earliest ways of improving computational speeds were quantizations, where you would take some code in your C compiler and you replace the floating points with some clever quantization of the floating point numbers, replace it with integer, then you can run it, then your program would already run a lot faster. Because 20 years ago, floating point units were very slow, right? Nowadays, that's not true anymore if you're running on a desktop GPU, on a desktop CPU or on a GPU. The floating point or integer, 32-bit integer multiply, 32-bit floating point multiply is just the same speed. So if you just look at the nanoseconds per instructions, it's very hard to see any speed up. So what else could we use? So if you do look at the results of quantizations, most of the time nowadays we're looking on considering the power usage, not the inference speed. Because even though a floating point, 32-bit floating point multiply is just as fast as an integer multiply, it uses a whole lot more gates and a whole lot more silicon on the chip, which means that there's a whole lot more electrons flowing through, so there will be, it will use a lot more power. About 30 times more power for a integer multiply versus a floating point multiply. And that is important for, of course, a lot of devices, computing devices that we have nowadays are mobile, like your mobile phone or your iPad. If you can reduce the power usage in your CPU to do certain inferences, then your battery will last a lot longer. That would be great, right? Also laptops. But even for high-speed computation, that's a win, because the CPUs now, if you run them at full clock rate, or the GPUs, they get extremely hot. And then you may have to throttle down the computation, because otherwise you would start damaging the silicon. So you can do a couple of floating point multiplications and they use a little bit of power and there'll be a little bit of a heat blip, but that won't be a problem. But if you do it sustained, your CPU is just going to heat up too much will wear out the chip faster. And also, of course, you need much more power coming into your data center. If you have followed the political discussions, mostly in the US, where now, well, at the moment, it's a bad time to buy a computer, right? I don't know if you noticed, but RAM prices have been shooting up. They've been going about twice as expensive. So if you want to buy a laptop, my suggestion would be to wait about 6 months until this data center craziness will have played out. Because basically all the RAM production for the next years has been bought up in order to build data centers to run AI, which, because they need to be cooled, require a ton of water and also a lot of electricity. But there's huge projects now by basically everybody, like Microsoft and Google and SpaceX. Elon Musk is wants to build lots of data centers. Now communities are fighting back because it lowers their quality of life significantly if you don't have water. Like it's, yeah. It's a little bit crazy to build it somewhere in Arizona where there's a huge desert, and now all of a sudden you have to use so much more water. So anyway, to evaluate the performance, usually we use power usage nowadays. Picojoule. Let me just. Now, there's basically two types of representations for numbers in modern CPU. One would be the standard kind of integer representation that you're used to, like 8-bit unsigned, 8-bit signed, 32 bits, 64 bits are common, where every position has this sort of doubles in the multiplicand for what you get. So this bit pattern, right, has an 8-bit integer. What would be the decimal value? The camera. Oh, yeah. What's this one? 0, yeah. Then, I mean, actually, I meant this nibble here, these 4 bits. So this is 2 to the 0, 2 to the 1, 2 to the 2, 2 to the 3, right? So this is 6, right? And here, so this would be 2 to the 4, 2 to the 5, 2 to the 6, and 2 to the 7. So that would be right? The sum of that, which should be 130, 160, 176, so 182. And you can represent it in hex form, in hex form, that would be A08, 8, A, B, 6. This is assuming that this number is represented as an unsigned number. How about signed? Signed is represented as 2's complement, right? Just make sure that I got that example correct. Pardon? I did this so long ago. It's like riding a bicycle. No. Okay, what did I have? $182. Okay, luckily I had that. So how do we? Unsigned would give us only positive numbers, right? If I want negative numbers, then what can I do? Want to change to 0. Well, one way would be to just have a sign bit, so we could take the most significant bit and make it a sign bit, right? So that if it's 0, then it's positive. If it's negative, then it's if it's 1, then it's a negative number. However, that has a disadvantage, because how do I represent 0 then? Because then 1, 0, 0, 0, 0, 0 and 0, 0, 0, 0, 0, 0 would both be the same number 0, right? With a fixed sign bit. So that's not a very efficient representation then. So we use the 2's complement, which means that here this tells us the sign, but we go 0, 0, 0, 0, and then the bit pattern in 2's complement, what would be 1, 0, 0, 0, 0, 0, 0, 0? That would be minus 128. Right? So in this case, we actually take, and this trick I actually didn't learn until, or, I mean, I knew this always, but I didn't learn this trick until last week, which is why I'm showing it. You can actually take the unsigned representation and just change it to this if you want to convert from integers, from binary to from binary to decimal. So here we have 0, 1, 1 and 1, 1, 0, 1. And then that would be minus 2 to the 2 to the 7 is minus 128, plus 2 to the 5 is 32, plus 16, plus 4, plus 2. Right? Just taking this bit pattern here. And then that would be 6, 22, 52, 54, 54, 28. This is minus 74, yeah. Right? So that would be the representation of this pit pattern as a 2's complement number. And we use that so that we don't have the 2 zeros problem. However, the representation then is not so nice in one respect, because the range of the data type, what's the maximum number I can represent as a positive number then? There will be a 0 here, because it has to be a positive number, right? And then the largest one would be all ones here, which would be 127. And it goes down to 128. So you have one more negative number that you can represent, as opposed to the positive numbers, which causes a problem if you have, if you want to calculate, for example, the absolute of a number, right? Because if your number is 128, negative 128, and then you want to invert it, then you cannot actually represent that anymore in your signed integer representation. Okay, those are the integers. How about floating point numbers? Floating point numbers are single precision floating point numbers would be 32 bits. And then you basically have 3 parts to the representation. One would be a sign bit, 0 for positive, 1 for negative. Then you have the exponent, and the exponent is basically how you can shift it. So this would be like 2 to the something that you can add there. 2 to your exponent. And then you have mantissa. So this here should be 7-bit, and I think this is 23 bits. This is 8 bits, and then this should be 23 bits. 1 plus 8 plus 23 is 32. There's a couple of tricks with the exponent. For one thing, it's biased, so it's added to minus 127 as the range, And the other thing is that the initial, this actually represents the first digit after the first one, because I could say, if I want to represent 16, right, the value 16, then if I want to write it in this kind of format, then I could say this would be a 2 multiplied by 8, right? So in this case, so here I have my exponent, so it would be 2 to the 2, 2 to the 1, multiplied, and then my mantissa would be 8. Or I can write it as 2 to the 2 multiplied by mantissa, then would be 4, right? Or 2 to the 3 multiplied by 2, or 2 to the 4 multiplied by 1. And they're all the same number, so that would not be a good representation, right? So now, if we look at these bit patterns here, then I'm wasting a lot of, I have 0, 0. If I represent this as a 4-bit mantissa, right, or 3-bit, 2 bits actually would be enough, 3 bits. Then the first one would be 0, 0, 0, 1. This would be 0, 1, 0, 0, 1, 1, 1, 0, 0, 0, right? For this exponent here that I want to store. Now, if I want to formulate that as a single representation, then we just say that the first entry here in the exponent always must be the maximum one I can choose, right? I want to use the maximum exponent here so that I can make my mantissa small. But if I do that, then here, the first digit, the first bit always has to be a 1, right? Because otherwise, I could multiply it by 2, and then I would get another larger exponent with a smaller mantissa. Right? So this initial 1 is implicit. So it's not actually stored in the floating point number. So that means we actually have 9 bits of exponent here. As far as our range is concerned, the first one always being a 1, and that fixes the representation then. So these are the details of floating point representation. What's the main difference though? Why is floating point, why go to all this trouble? If I look at the numbers, right, from negative infinity to infinity, then this would be the entire number line. So any point on here, there would be pi and 2 and 1 and 1 over e and all the numbers that we're familiar with, right? Now if I look at the integer representation, then there's only certain bit patterns that I can represent. So with an integer, I wouldn't be able to represent 3.14. I wouldn't be able to do 2.5, right? Because I can only go 1, 2, 3. There's no 2.5. So if I look at this, then if here is 0, then what numbers can I represent using integers? Well, in the positive side, it will be some range like this. Right? And depending on what my the width of my integer, that then depends how far I can go up here. For 32 bits, which are popular nowadays, this range here, this number, the top number here, will be 2 billion. Right? So pretty large number actually. And it would the same thing going down. And the smallest I would be able to represent would be negative 2 10 to the 9 minus 1. Because there's this extra 1 pattern that I can do. Like here we have negative 128 to 127, right? How about floating point numbers? What would the picture look like for floating point numbers? Many more numbers, and why? Yeah. So for floating point numbers, here the difference is constant, right? This is always the same, always 1. For floating point numbers, that's not true. So for floating point numbers, goes like this, and then it basically doubles every part of the exponent. So it's like 1/8, 1/16, 1/8, 1/4, 1/2, 1, 2, 4, 6, 8. So they get multiplied out like this. So the ranges greatly increases. So the maximum number that I can have with a 32-bit floating point is something like 2 to the 159 or something like that. A crazy high, or pretty large number, not crazy high, thanks. 3.4 times 10 to the 38 even. Right? So this is a very, very large number. But around there then, I don't have many numbers. There's like a huge gap to the next number then, to the smaller number. So here, the distance keeps increasing. Get rid of this one here. So that's the main difference between floating point numbers, and that's really what should guide you whether you pick an integer or floating point number to represent your data. Just because you have floating point numbers, like just because you have to represent 2.5 doesn't actually mean that you have to use a floating point number. Right? It's just if you need to represent a range of very large numbers. So let's say you're in a robotics domain and you have a playing field that's 2 meters by 2 meters, and you want to represent the position of your robot in X and Y. there's no need to actually use a floating point number for this, because if you have in fact, it would be silly to use a floating point number. Why? Because if I have a 32-bit integer, right, then of course the standard representation doesn't make much sense, because I could only represent 0, 1, and 2. So there would only be 3 positions that I could measure using my integer. But of course that's not what you would do. You would use fixed point integers, and then if you know that your playing field is between 0 and 2 meters, then you would say x is equal to you would just take your 32-bit integer and divide it by 2 to the 32, but we need to represent from 0 to 2 meters, so multiply by 2, which will be 2 to the 31, right? So let's just, should have this is using the wrong camera, I think. Or no, not this. Now I want to show window left. So about 4 billion is what I can represent using 32-bit integers, right? So I can go from 0 to 4 billion, then divide that by 2 meters. Then it's this many then each step is 10 to the minus 9, right? So I can represent, so that will be this many millimeters, this many millimeters, this many micrometers, this many nanometers. So we have huge range in this case, right? Like I could represent the position extremely accurately, way more accurate than any robot ever could do in the real world. Like on nanometer, and this is how much light travels within a nanosecond, right? So it's a very small distance. So just because you have a value that requires some floating point numbers, you can use fixed point integer arithmetic in order to do that. Or, so here we range it to the maximum value, and x would then just go up with 1/4 billionth of a meter. Or, in this case, if I have 2 meters, then I also can just say that the first bit is, or let's make it 4 meters, then the first 2 bits are the meters, and everything else is then in the floating point of the meter here, right? So in this case, I would still have 30 bits per meter to represent my distances. And I would use the whole range of my data point. Now, if I wanted to look at the number of digits, number of floating point numbers, I only have 2 to the 23 as opposed to 2 to the 32. So my floating point number representation would actually be much coarser than the fixed point integer would be, right? The difference being that if I ever get a number and it's 3 meters, then fixed point integer would just blow up. There's no way to represent that anymore. But your floating point number could still represent that even if the robot is 100 meters away all of a sudden. But the precision with which it can detect these positions changes dramatically. Okay, so now I would like to try something. We could apply the quantization to neural networks, but it's not very clear what will happen. Like there's no intuitive result for, or kind of intuitive recognition for what changes are actually happening to the network, except that the weights change. But what impact that will have, you would have to run an experiment like testing it on a bunch of queries and things like that, which of course we could do, but I want to try a slightly different approach. For this, and that is, instead of quantizing a neural network, I would like to quantize an image, because then that's something visual and you kind of can have a look at it and see the result. So Yep. I mean, I usually look for images in Taiwan. Uh, which one is copy? This one? So, uh, how did I? What was the website that I always used for pictures? Pictures. No, 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 no. There used to be a website that I always forget it. I haven't used it in a while. No. Um, no, all the channels. Do both. One convert it to grayscale first, then make the thing smaller, the grayscaled image. What is this? Pixel, pixel thing. Postimage.cc. Yes. think I have OpenCV in here. I think I do. Yeah. And then OpenCV, of course, loads the images in the wrong order. So we need to them. And here's our picture of Taiwan. So now I can also make the grayscale version. So I can do that using the CV function, cv2.convert color space. So 1 row, 2 columns. Convert color, yes. Let's call that color image. And we have to specify the color map. CMap is gray. So here we have the two pictures now. One is RGB and the other one is grayscale. me. I can turn off the axis too. Um, Okay, so here are the two pictures. Now implement the quantization and then show the 1, 2, 3, 4 pictures that you would get. Yeah. Mm-hmm. Green, yes, yeah. That's the default color map. No, this is a color image. You can specify a different color map, I think, which will do some remapping of the color, but usually you don't in this one here. But for a single channel, you always have to specify a color map. Because there's different color maps that it has for different usage. So some of them are to kind of give you an idea of where all the points are. Other ones show you diverging colors, like the differences between 2 pixels are highlighted. There's a whole science of color maps for scientific visualizations. So let's work with the color image, or I'll work with the grayscale image first. And I have 1, 2, 3, 4, 5, 5. Okay. 2 rows, 3 columns. 1 will be the grayscale image. One, 3, 7. Actually, before I do that, let's just look at the data type for the color, for the grayscale image. the shape. So this is unsigned integer 8 from 0 to 255, and the size is 800 by 600. So I have I have 3. That clears out the least significant bits. FC, FF is 111, FE. So then the next one would be F, be C. And then just the largest bit, which will be 8. And that would not be mask, that would be this here, image. This would be I plus 2. So then it should look something like this, except I missed one here. And then this is what I get. And then you can do the same thing for the color image. Go. Done it already? Okay. What I want to do is I want to reset. I want to take 8 bits and convert it into a 6-bit, 4-bit, 2-bit, and 1-bit integer, right? So what I want to do is I have some bit pattern. 1, 2, 3, 4. 8. 1, 2, 3, 4. And we said we want to get rid of the least significant 2 bits, so I want to replace those with 0, 0, right? And that converts it to int6, because now I only have 6 bits left, right? And if I want to do the conversion into 4 bits, then I want to take those unchanged and replace these with 0, and then that will give me int4, right? And in order to be able to clear a bit and set it to 0, I can do an AND, right? And if I want to do an AND, then I would have to have a bit pattern where this one is all ones, and I do an AND of this pattern, then I will get the correct int6 value. So if I want to clear off the last 2 bits, I have to use this bit pattern, which in hexadecimal would be F, right? 1111 is F, 1100 is a C. So that gives me FC, right? And for the next one here, I would get 11111. 0, 0, 0, 0, which will give me F0. So that's just what that code does. It just goes through and sets up the bit masks. And I mean, we're cheating a little bit by using images, right? You can see that even with a single bit, I still can actually recognize a lot of the image, right? Like, it didn't really lose that much, and we did a compression by 90%. We got rid of 90% of the data now that we could have used. So that's pretty interesting, I think. There's some details that are left here, like the shadow in the road looks weird, right? On the 1 bit, because that that thing here, that what do you call it? The thing in the road to go into the sewer. Anyway, that's gone now. After this compression here, that part here is not seen anymore. Also, the clouds are gone, which is actually okay, I guess. If you do need to do a compression, the clouds are the least important part. But here we still have some detail even in the forest. This one here, the house is all black by now, okay. but you can still recognize the objects very easily. However, this is a very simple approach to doing the quantification. Let's look at one bit and see if we can improve that a little bit. So if you wanted to be able to do a smarter way of doing the quantization, then what would you actually need to look at? Well, I really would like to know how the data is spread out from 0 to 255, right? And one way we can do that would be to actually plot the histogram. And that will give us a lot more information about the image. Now, because, for example, if I now take this picture here, this picture worked quite well, right? Our compression wasn't so bad. But now, if I increase the brightness of the image a little bit, then what would happen? There would be more white, yes, but I would also lose detail then in my image, right? So in the most extreme case, let's see, if I take the image and okay, yeah. So now we'll do the same thing. We run the same code. But after I have the grayscale image, I'll do some... Actually, let me try. This one here is actually... I think I can do this in one CV call, in one open CV call, to do the masking. Let me just try that. Okay, let me have a look. Mm-hmm. Yeah, but then you did the 3 color channels independently. Yeah.
Also the clouds are the first.
Mm-hmm. The first thing to go. Yes. Yeah.
And then yeah, like the overall brightness.
Mm-hmm.
I guess because my picture is very like
A lot of
colors.
low. Yeah. Yeah. That's okay. But this is very good. Yes. So we'll look at that after we're dealing with more intelligent quantization per channel. But yeah, that's exactly what would be the next step that you want to implement. But now let me just change the code here. So one thing I wanted to try is so here's our code to do the decimations, but now, before I actually plot the image, I take gray is equal to gray divided by 2. 128 or 127? 128. Okay, so now I have different output, right? If I modify the image, then here the last two are basically useless. And the changes that I made were actually pretty straightforward. We wouldn't actually have lost much information in this. It would have been just deleting the least significant bit. But I shifted it all above 127 now, which means that for 1-bit quantization, where I just use the standard range, then that wouldn't give us a good image at all. So nothing we can quantize there anymore, because everything was above 127. So everything would be in map to white. So the last image here is just almost completely white. Actually, so I guess I should have made it 128. Yeah. So now, okay, now it doesn't paint it as, if everything is black, then it just points, everything is, it just maps it to black here. So, whereas these images are still okay, the next one here, the next higher resolution would just be useless. So if I wanted to improve that, then what we can look at would be the histogram of gray and bin it into 256 bins. And this is what our histogram looks like. And this is the resulting output then for the grayscale image. Now, how would you use that information? Or if I look at it, let me do another one. So here you can have a look at the histogram. This is the original unaltered image. And then this is after I shifted it all to the white side. Right? The shape of it is still the same here. Right? But it's also clear that if you have this kind of input data, this kind of histogram of your image, then representing it as 2 bits, one is left and the other one is right is a crazy idea, right? Because you lose all the information. Because there's no pixels here. So just looking at this picture, where do you think we could optimize? Like what would be the histogram where it would be impossible to optimize something? That's right. If every pixel occurs exactly 1/n times, then no matter what you emphasize or de-emphasize in your quantification, there's nothing you can do. You're always going to cause the maximum kind of disruption in the image. Looking at this histogram here, which parts should we focus on? Correct, yes. So this area here is very important. We have many pixels in this range, not just the absolute number in one column, but also around it, right? So there's a whole bunch of it. So that seems to represent a lot of detail. Here, there's not much we could do. These ones are all feel relevant. There's only like this little dip and a little bit of a dip towards the end. So if we wanted to do a smarter way of doing the quantification, then we would focus on this area on the left here and reduce the impact of the area on the right here. But not, that's I guess why it works so well if we just do the standard quantification on the least significant bit. There's no obvious great imbalance in the image, whereas there's a huge imbalance in here, right? So here we definitely want to ignore all of this, right? But that's because I generated it artificially. This one here is the natural image. So show the histogram for your image and the other images that you created yourself. Multi-class angel. No support vector machines. Do this while you're here. Okay. Yeah, you can do that too. I wouldn't do that though. Because you know what these operations do? Go back to the slide you had before. The screen you had before, the other tab, the other app. This one, yeah. Do you know what this does? But why? Okay, but why? What does this line do? It is, but why is it just like this? Yeah. Yeah, like what is this? This operator. Kevin? Yeah? What does this do? You guys don't know? No, see? Okay, Elena, please, what does this do? Yeah, so this is a shift left operator. So that means you take the data, you shift it 2 positions to the left, right? And then the question is, what does it put in the first 2 bits? That depends, not necessarily. It may be the 1 if it's interpreted. If it's interpreted as a signed integer, then it would be, would add a 1 in the beginning. And so then what happens is you have 8 bits, you shift it, so the 2 significant bits, you shift it to the right. First you shift it to the right. So these 2 bits are thrown away, right? And then you shift it 2 to the left, which brings it back, but it fills in the bottom part with zeros. Okay, this is how this works. This is how this is supposed to work. The problem with this is I never trust it. I never trust the... I know how AND works, but for the shifts, there's actually 2 versions. So one of them is, when it shifts to the left, what does it add at the most significant bit when you do a shift? Does it do a sign extend, which means it would add whatever the sign bit is, or does it always add a 0? Now, there is, if it's a logical shift, then it should just add 0. If it's an arithmetic shift, it should do a 1. Also, when you shift it to the right, CPUs have the shift operation, which would add a 0 in the least significant bit. But sometimes you have the rotate operation, which takes the carry bit and puts it in there. So I think it's standardized now, but for a while it wasn't clear in C what would actually happen. And these are all based on the C language. So I'm never sure exactly what this does, so I like to use AND because I always know how AND works. Here, it may depend on which programming language or which library or which compiler you're using, and you may get some unexpected results. So I'm not it's not faster than doing the AND. The AND is faster anyway. But I never trust the shifts because you really don't know what, especially the shift right, I'm never sure what the data actually will be interpreted as. But now it's in the standard, and if everybody would implement it, I think the standard is now clear about what it's supposed to do. I'm sure it is, but if all the people that wrote programming languages and implemented the shift operator, if they all agree what it should do or not do, I'm not 100% convinced. Whereas AND, everybody knows what AND is supposed to do. There's no ambiguity. But there are some, yeah, shift will also work, I guess. Yes. Okay, yeah. Okay, yeah. So we would want to focus on this part here, right? That's kind of stuck out. And that's for the grayscale or the color?
That's for the color, my RGB image.
Okay, and then you want to do this histogram, but you want to overlap the histogram for RGB because we may be able to, that would be more interesting. Yeah. Mm-hmm. Yeah. And so you can do that, and then it'll look very nice. So let me just see how to do that, histogram. Oh, I think you just call histogram multiple times on the. Correct. So if you put if you put on the same axis, if you add multiple histograms, it'll merge them. So that's actually all you need to do. It's easier than I thought. And you can set a transparency. Let's do the histogram for the color channels, the color image. And I have to say, I'm actually a big fan of the matplotlib stuff. You can make very nice visualizations that are very useful pretty quickly. So we have range 3, then ex2 dot histogram color image. Yeah, that is right. So this is what I get for the color image. What does yours look like? Okay, and let's have a look at your image. Okay, a lot of blue, yeah, yeah. And then you have not much. Yeah. So then what you want to do is check this part here. There will be few pixels in there, right? So you could just implement mapping that all to the same value, which would reduce the size of your histogram and your color image then by 50% already. So maybe just try that. So just iterate through it with the loop, and then if it's less than 130, just set it to, I would set it to 65, which would be halfway between the range that you collapse. And what can I do at my image? Harder, right? Yes. Why did I take this one? I should have taken yours. There doesn't seem to be such a, I mean, for me the tape off would be at the top. So let's take 160 and replace it with 160 to 255. 210. Two two one. So here we have that. 223 and 224. And then what I want to do is I want to take the image 1, the color image, So here I squashed 16% of the pixels. Of the data, and this is my histogram now. I wanted to set the Y limit though, so that it's 20,000, 10,000 maybe. Okay, so now we have that. Now it actually is pretty flat here. And then of course this is the whole area that I replaced, 16%. And not that much difference actually in the image, mostly in the sky here. I think. Okay, yeah. And then your output image.
Okay, here it is.
Okay, yeah.
This is the original, this is the output.
Go up a little bit. Yeah, not much difference, right? That's pretty nice. And the rest of your histogram looks okay too. Yeah. Just take this part, yes. That part, of course, would be unchanged. You would expect that. Okay, yeah, okay, good, yeah. And you can see, like, it's surprising. It's surprising what your visual system can do, right? Because even at 1-bit compression, I can still see pretty much what that image shows. Some of the details, of course, are lost, but you'd still see kind of like a wooden landscape with a river in the front. So that's different when we are dealing with neural networks, I think, because you can look at the floating point numbers, but they won't make any sense to you, right? The distribution of the numbers. I guess that's why I think it's kind of nice to work with the image. Okay. Show the quantizations, yeah. Now, there are actually image formats that you may be familiar with, or you may have heard of, that are using this idea. So if you're dealing with an indexed color image, which nowadays are not that popular, but 30 years ago when you had a 4 megabyte machine, then a large image would have already blown your entire RAM. So people tried to come up with better ways of representing images, and one of them was especially for clip art and like artificial images, you would only use a couple of colors. So you would have indexed color formats where you have a maximum of 16 colors, and those you had to choose. But you could change, you could set each 16-bit color image to one of the 32-bit color values that you want, right? So then you would take a 24-bit value and convert it into a 4-bit value with the lookup. And that's the same format that we would do using neural networks. You can do the same thing. So you can group weights into different classes and then have a lookup table that says class number 1, the weight is 0.1257 times 10 to the minus 3 or something. So you don't actually, if you want to do more compression, then this kind of remapping of the color, the line here, the number line, which is really what we're doing, is not sufficient, right? This works well in natural images because if you have a high count in the original image here, if there's a very high count here, there's also a good chance that the other pixel values will have a high count in a natural image, right? But in an artificial image, that's not given, because I can paint with pure red and then I can paint with pure white or pure blue, and there would be no overlap, no intermediate values between them at all. So in those kind of images, it would be better to have certain number of sort of points that you can set, and then that's where you would map your ranges to. That would allow you to do the distribution of the images non-linearly. Like right now, we're kind of mapping linear values to the pixel values that we represent in our histogram here, but that has its limits, right? If we do one step of indirection, where we use the class as a lookup value to some actual weight setting or actual pixel value, then we can do that better. But the question is, if I now want to say I want to replace this picture here, and I only want to use 8 colors, but the 8 colors I can choose from any of the 8-bit red, green, and blue values, then how would we do that? Or if I say you can only choose four colors, then where would you put them in this particular histogram or in your histogram? Yeah, if I had 4 peaks, then that would make sense, yes. Or the 4 highest peaks, yes, yeah. But of course, that's a lot of work. If I ask you to do 32, then that would be already more tricky. And so is there any algorithm that you know that would help you choose the best 4, for example, or the best 8, or the best 10? So what we want to do, we would want to have pixels that all have the similar value where the integral of this should be maximized, right? So it may not be the peak. Also, if I take the maximum values in the histogram here, then it would give me 1, 2, 3, 4, they would all be here, right? Which is not what you want. You want them spread out, right? So that the area that they correspond to would be the maximum number of pixels. So computationally, that would be an expensive algorithm. You could calculate that, and if you have 4, then it's probably not too bad, but you still, there's no way to do that any better than just have 256 choose 4 and then calculate the score. So that would be computationally very expensive. That would be 256 times 255 times 254 times 253, 1, 2, 3, 4, divided by 4 factorial, right? So that will be 2 to the 8, 2 to the 8, 2 to the 8 minus 1, 2 to the 8 minus 2, 2 to the 8 minus 3. So this, for all intents and purposes, this could be, we can ignore the minus 1, minus 2, minus 3 there, because they don't add that much. So that would be 2 to the 32 then, 8 plus 8 plus 8 plus 8, divided by 16, so 28. So that's not a feasible algorithm for trying. Right? So we would need to have a different approach. The algorithm for doing that, any kind of problem like that, would be cluster. The problem is called clustering in the general sense, because you're trying to take this histogram and sort of group it into packages, and the most common algorithm for doing that would be k-nearest neighbor algorithm, right? And how does that algorithm work? Correct, yes. There's 2 steps in the k-nearest neighbor algorithm. One is kind of an evaluation step, the other one is an update step. So it's a gradient descent algorithm on the loss function or gradient ascent on the quality of the clusters. If you have some clusters, and let's say your clusters are like this, then it would actually work quite well, because this data set is easily clustered. Of course, it's much harder if it looks like this. Correct, yes. So first, we have 2 we pick 2. If I have 2 nearest neighbor, if I calculate the 2 nearest neighbor approach, right? Then I take 2 centers, center 1 and center 2, and then it calculates all of the ones that belong to C1 and all of the ones that belong to C2, which is where the nearest neighbor comes in, right? So the ones closest to C1 will belong to C1, and the ones closest to C2 belong to C2. So that would mean that in this step now, this one, 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 these ones, all belong to C1. These ones all belong to C1. This one belongs to C2, right? And now we calculate the average of our classes for C1 and C2, and then we move C1 to the new position. So what will be the average of this area here? Maybe here somewhere, right? Then it will move to there. And here I only have these ones, So C2 will move to here. And then the algorithm repeats itself. So now I have a different cluster, so it will take these, but these ones now, this one will not be, will be closer to C2 than C1. These ones here will be closer to C2. These ones will be all still belong to C2. So that's the k-nearest neighbor algorithm. And it actually works surprisingly well. It's a very efficient algorithm. It's definitely an algorithm that you should know and understand because it has many different applications. In particular also for quantization of language models. The only tricky part about k-nearest neighbor is like you can implement this once and it'll run forever. It'll run in many different problems. It's really nice to use, except what is K, right? If you cluster the image and you say, I need 4 output classes, then K is 4, because you choose it, right? And then that's fine. If you have a picture of the cards and you don't know if there's 1, 2, 3, or 4, or 5 cards, then that's a lot harder because you don't know how many cards are actually in the image. So if you want to cluster pixels to map them to the cards that they belong to, then that doesn't work so well. So anytime where you know what K is, so you select K, for example, we have 24 bits of information for every pixel. I want to bring this down to 8 bits. Then you know K is going to be 2 to the power of 8 in this case. You would have 256 different clusters you can use. If you want to bring it down to 4, you set it to 4, then okay, you have 4 clusters only. If you don't know what K is, then it becomes tricky. Then usually people look at starting with K of whatever they think is reasonable, and then they calculate the K nearest neighbor clustering using K and K minus 1, and then see if they can drop one of the clusters without losing too much information. And it's kind of like a meta heuristic for how to select K. But if you know what K is, and in quantization we do, right? We have kind of a target in mind. How much we want to reduce the size of the network, then that works great. And so you can try the clustering for this particular image. Just run K nearest neighbor, and for this kind of image, it's surprisingly good, even if you just have like 10 different colors. It can do an amazing job matching, usually for real images. They start to look more and more artificial then, though, because all the shadows and shading will be gone, right? Blue, everything blue in that image will be one blue, not different levels of blue. But for that kind of thing, you can get extremely good compression ratios then. And for neural networks, this is also one of the most common ways of quantizing the input. This, however, if you do this quantization and then you have basically a lookup table, what the actual weights are, then that compression is mostly for the size of the model on the disk. You can greatly reduce the size of the model on the disk. During the actual computation, though, it doesn't really help you that much, Because on a GPU, you wouldn't be able to do that indirect lookup of what the actual weight is. At least none of the GPUs that I know can do that, this extra step of indirection. If you do it on a microcontroller, then yes, that would slow it down though, because you would have to, you get like your weight is 7, but it's not really 7. It's look up the value of this weight in this table of possible weights, right? So there's one extra level of indirection which usually slows it down. So inference speed would usually decline, but size on disk can be greatly reduced. Okay, good. Then that's it for today. So next time we'll continue with quantization. And in the afternoon, we will talk about the assignment with the robot. So hopefully you can match up with your German students and talk to them about driving the robot. You already have the vision program. So as long as those guys can get the robot to the right place, you'll be able to tell us which one was rotated. I always wanted to have wheels on my computer. That's why I ended up in robotics. Yeah, yeah. Mm-hmm. Yeah. 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 Hopefully you can work together with them, yes. Then you have to post a message in the big blue button and then we can assign you somebody. No, I'll ask Reinhard then. You have to make sure I notice the message.